Hello, I forgot to write my name, sorry for that, but it's pronounced as Canberk. So I'm pretty sure everyone will remember it after this presentation. And today I'll be talking about the usage of graph neural networks for like multivariate time series anomaly detection, and like in general and also in particular, we also applied it on the Kungsbacka bus data. But one specific bus particularly towards the end of my presentation. But before that, let's talk about why do we need GNNs or graph neural networks on like any type of, let's say, time series task. Like why this type of this family of models may be useful for us. So why not an RNN? Why not a transformer? So the reason is that like by using this graph structure, you can bias your network, your let's say neural network into eliminating let's say unneeded interactions or like spurious correlations between different time series features. So as your dimensionality of your data set increases, you also run into the risk of these like spurious correlations between different time series. But with the help of a graph, assuming that graph is useful for your downstream task, you can constrain those interactions between particular sets of features. So, for example, here you see a red node here, which are like quite far away, 2 hops away from the blue node, and their interaction is limited, like through this. Let's say I don't know, they still interact through this node, but the interaction strength is much lower than between these two. So with the help of this, you can somehow mitigate this curvature dimensionality problem as you increase the dimensionality of your data. So this comes in handy because like in cases where you don't have a lot of data, but like a lot of observations, that using a transformer is not really meaningful. Like in those cases, you can use a geometric structure like a graph as an inductive bias to just like learn efficiently with from the amount of data that you have in your data set. This being said, like let's go into like one use case of GNNs, and that use case is like anomaly detection, like time series anomaly detection. So there are so many models, of course, like graph neural networks is relatively new, but not so new. So there are many approaches that are proposed, but this model, like called graph deviation network, is one of the earliest ones and like one of the most commonly used ones in the literature so far. So like it's quite well known and it's like used as a baseline in many other, let's say, many contemporary research papers. So the benefit of this is that like it can learn the latent graph from your multivariate time series data set in case you don't have the graph ready for your multivariate time series data set. And it can learn this latent graph directly from the data. And like as we all know, like a graph neural network operates on a graph. So we need a graph to just like apply it. So learning a graph is very important for that reason. But we don't need to know the underlying real graph. Like we just need to learn a graph that is useful for our downstream task. So how does it learn? So assume you have n features in your multivariate time series data set, and the graph deviation network starts with randomly initializing n vectors for every feature. So imagine all these, let's say, values, all these like time series are coming from sensors, and you have n sensors, and you randomly initialize one vector for every sensor. After this initialization, you compute the cosine similarity score between every pair of features, like between this orange one and this blue one, between this orange one and this green one, and if there was a, let's say, another feature here, between this orange one and this feature, and so on and so forth. And after you obtain those like similarity scores, then you rank them, and then you select, say, k highest similarity scores from those like from this list of similarity scores. And the features with top k highest similarity scores will be your neighbors for this node that represents this feature. So you can see a graph like this. You can see one example graph here. So you learn a directed graph. And after you learn this initial graph, then you use that graph in your forecasting module. This is the third module of this framework. So you use a graph attention network to obtain some forecasts, and then you feed those forecasts into an anomaly scoring module and get the anomaly labels. So some of you may be asking that, like, we initialize the features, we initialize the vectors randomly here. So how can we know that this graph is good? Like this may be a completely gibberish graph. And that is true. Like in the initial stages of your training, you're not learning a good graph. But what this framework is doing is that, like, it uses these vectors in the final output of this module, in this forecasting module. So that way you can backpropagate the loss and then fine-tune these vectors and then fine-tune the graph as a result of it. Because as you fine-tune these vectors, this similarity metrics will change. What we assume here is that, like, you are backpropagating the loss in a nice way, that you can, like, get this like you can get a nice signal so that, like, you can change these like vectors in a good way for your, let's say, learning task. And as you can see here, like I just like already mentioned this, so these v values are coming from the vectors here, and these values called like z are like the feature representations that you get in the third module, in the graph attention network module. So you just like element-wise multiply them, feed them into another neural network, and obtain the predictions for this one. And then these predictions will be fed into the fourth module, which is the anomaly scoring module. And the anomaly scoring module will compare the true values with predicted values. And based on the differences in errors, it will label the row, like this observation, as anomalous or not. So, set of explanations so far. Like just before going into the experimental results, I want to just like make a quick description of this like graph attention network. What is a graph neural network, and so on and so forth. In case you don't know, you haven't heard about them. So they are basically mimicking the convolutional neural nets as we know, but it is doing differently than CNNs. Is that like you don't have any filters that we use in CNNs. In a graph neural network, you have one node and then you have a set of neighbors of that node. And in order to calculate the new feature for that node, in order to transform the features of this node, you multiply all the features of the neighbors with a weight matrix, and you multiply the feature of this node with another weight matrix, and sum them up, feed them into a, let's say, nonlinear function like ReLU or sigmoid, whatever, and then you get the new representation for your node. And you do this for every node here in your graph. You can either use a different weight matrix for the node in question and the node neighbors, or you can use the same weight matrix. It completely depends on you. And in the graph attention network version of this, I just talked about graph convolutions here. You also score the neighbors. Like you also just like parameterize the edge weights here. so that you can filter out what neighbors are like more important for this node and what neighbors are like less important. And you learn this, like you learn this filter with the help of this attention score. So getting back to the graph deviation network, so the original authors applied it on two different high-dimensional data sets that are taken from a water treatment plant. And they use several number of, let's say, like other type of approaches, which are like variation autoencoder based, generative adversarial network based, or like Gaussian mixture model based approach, and some, let's say, very simple baselines. And in both data sets, their methods performed the best. Like it had the best F1 scores. So this, coupled with the results from last year's Scania competition that was presented in EDA conference, we thought about trying this method, this graph deviation network, on one of the buses in Kungsbacka datasets. Because they were quite promising, and like we thought, why not? Like let's see how the result, what type of results that we are gonna get. So you can see the features of the bus here, like one of the buses here. So we took a subset of all the data sets that Danny just like presented. Since this data set has very small number of anomalies, we also needed to inject some sort of, let's say, failure scenarios into the Hazel data set. And for that, we created 3 different failure modes. One is engine failure, the other one is gearbox failure, the third one is brake failure. And at every different scenario, let's say in engine failure, your feature for engine speed, and also your feature for fuel rate, and also some other features that are related to this scenario, to the engine failure scenario, will be affected at the same time. And same goes for brake failure. So when brakes are like, when there's a failure with the braking system, the wet tank air pressure will be different than, like, we'll have like anomalous values than as compared to its normal values. The brake pedal position will have a different value. The vehicle speed will have a different value, and so on and so forth. And you can see them. You can see some of them here. So the red lines represent brake failures, and like this is like this time series is for like engine speed. So when there is a brake failure happens, the engine speed doesn't, like it's not affected because it's not related to this failure mode. But when there is a failure with when there's an engine failure, the engine speed increases abruptly. And similarly, when there's a failure with the gearbox system, the same thing happens. Like RPM values for the engine also increases. And this time series represents the fuel rate column. It's just like the only difference between them is that in this case, we tried to inject a bit more obvious anomalies than in this case. Like these anomalies, we tried to make them a bit harder to detect. But I don't know how, like, I don't know if we succeeded in this or not. So the results, like the initial results that we get is this, which are not really nice. Like not the results that we expected, because like one reason is, of course, like one way of seeing it is that in the easy data set we are getting a much less F1 score than the medium one, although this had a lot of, let's say, standard deviation. And in general, the F1 scores are like not so high, like they're pretty low values, which we think that like it is due to this, let's say, this script that we injected anomalies, because here I'm only doing some random walk, and then just like I take these values from this random walk and multiply these values with the healthy values here. with the health values in the original time series. Which may not be the best approach to just create anomalies. They may be like I may be injecting, I might have injected two simple ones. Lastly, so besides the fault besides the potential fault with this anomaly injection code, the small dimensionality of the dataset might have also affected the results. So what I mean by this is that if we had maybe a dataset with higher dimensionality, we might have seen a bit more benefit from this graph deviation network, because as I told you in the beginning, as your number of features increases, the graph neural network, like the use of graph neural network, may also benefit you because it's more suitable with dealing with curves of dimensionality. Secondly, like the other reason may be due to this some issues with the graph structure learning component of this framework. So there have been some criticisms of its approach for learning the latent graph, like this embedding based approach. And that is mainly because like there is no way to just like to really understand if you are really back propagating the loss all the way to the embeddings, so that like you can hone the graph, you can fine tune the graph as you move through like one training epoch to another training epoch. Nevertheless, we are still working on it. Like we will just like try it on, let's say, data sets with better defined anomalies, because this approach is promising, not only on the original paper, but also on the last year's competition on Scania dataset. And hopefully we will get better results in 1 month's time or like 2 months' time. So that's all.
Thank you.